Okay, good morning. Today's lecture is sometimes motivated by interactive proofs. We'll talk about interactive proofs in this context soon, maybe even this lecture, depending on how far we get. But there's another way I like to motivate this lecture, and it'll motivate something we'll do next time, which is to imagine the following. What if we decided at the beginning of complexity theory that efficient should mean BVP? So somehow we decided, in the olden days that efficient was polynomial time, but the deterministic polynomial time. But what if, in reality, like randomness is pretty cool. So what if we just decided that BVP would be like our base notion of efficient? So that would change these things in complexity theory. And one thing you could ask is like, okay, then, what would NP be? What would be the new NP? And there's a couple of different possibilities. So I'll tell you two different complexity classes that arguably would be like the analog of NP in this world where everything was always randomized. One possibility is a certain complexity class called MA. We're going to be discussing two complexity classes today, mainly called MA and AM. As always. So this is, honestly, this is probably a little bit more natural. So in this world, it's like the prover verifier certificate version of NP. Like a prover gives a purported certificate to a verifier. And then the verifier checks it, tries to accept or reject it or confirm it. Okay, except that normally this is, the verifier, the checker, is like a polynomial time algorithm, but now we're letting the verifier be a randomized polynomial time algorithm. Okay, like, it's check only, is either says yes with probability at least 2/3 or it's probably at most 1/3. Okay, in this story, or like the title of this lecture, this prover is sometimes called Merlin. Because, I don't know, it's like a wizard, he can figure out anything. And I guess Arthur, so I guess Arthur's a human, so unlike most humans, he has access to random points. I don't say that actually, I think these names were chosen by Latsi Babai. And I think he was like also in the back of his mind thinking that this stands for max, M stands for max, and A stands for average. And then it was like a coincidence that these Arthurian names for them too. So, right, let me say it more formally. And I guess I'm sort of defining a complexity class now. You would say that L is an MA if the following situation holds. Whenever X is in the language, there exists a certificate Y such that this, verifier, let me say, A, xy equals 1 with high probability. And when x is not in the language, for all purported certificates that Merlin gives, Arthur says no, or 0 high probability. And maybe that high probability can be at least 2/3. And the point is A is now randomized.
A should be inside the quantifier, right, as well. There's this Y and A.
Yeah. Well, language L is an MA. If there's a randomized, there's an existence up here even. If there's a randomized polynomial time Turing machine A, taking two inputs, X, the real input, and Y, the purported certificate for something, with these properties. And let me actually slightly expand on this. So this is a randomized algorithm, I'm imagining. Let me do the trick of like imagining it as a deterministic algorithm that takes some like random coin flips as an extra input. So there's going to be 3 inputs now. So I'm going to change this to such that for most Z, think of Z as like random coin flips. B, X, Y, Z, equals 1. And now this is a deterministic machine. Okay. So the same thing, I just did the switch of thinking of a randomized algorithm as having like an external random coin input. Okay, so I'm going to write the same thing here. So that for most z, v, x, y, z equals 0. Okay, so this is the definition of the complexity class MA. It's like NP, but like the randomization or the certification algorithm is allowed to be probabilistic with bounded error. And let me just make a notational comment for the rest of the class. I'll hold in this class. I'm going to only write exists y, but what I really mean is there is a polynomial such that, okay, so like in this class, exists y is this thing that in the previous lecture I was calling exists py. So it means there is a polynomial p, and exists y means exists y such that the length of y is at most p the length of x. And here, like this z is also bounded in length by a polynomial in length of x. And like whenever I write v, I mean like a polynomial time algorithm. So I'm just going to stop writing like polynomial bounds everywhere, but like everything is polynomial time. Okay. Sometimes people call the MA like the class of languages that have publishable proofs. It's like Merlin for like one time can like write down the proof on a piece of paper, and then like humans who have access to randomness can go and like try to like verify that. Okay, so that is one sort of notion of a randomized version of NP. Let me tell you the other notion that you might come up with. This is slightly less natural, but it's important in the complexity class. It's called AM. And here's one way you can motivate it. So recall a basic fact, I guess it's code 11, that a language L is an NP if and only if L has a polynomial time many-one reduction to set. That's a fact that we know. And now, like, if we decide that efficient means randomized polynomial time, well, there's one algorithm in this statement, one polynomial time algorithm, the reduction. So we can imagine, like, now let's let this be randomized. Reduction is randomized. Okay, so what that means is, like, given a string x, the reduction outputs a string y, and like, it should be that with high probability, the answer to whether y is in SAT is the same as the answer to whether x is in L. Okay, so another way to put it is, L is in AM, means when x is in L, it should be that like R of x, this is like a randomized reduction algorithm running on x, is in SAT with high probability. And similarly, when x is not in L, it should be that R of x is not in SAT with high probability. And let me first rewrite this again in this notation. Instead of thinking it's a randomized algorithm on x, I'll imagine like taking the coin flips out as a second input. So I'll say, cross this out and say for most y, r, x, y. I use the same notation here for r, like r with real input x and random coin flips y. Now r is deterministic, is in SAT. And I would write the same thing down here. In fact, let me expand, I know it's a little annoying, but let me expand this out too. What does it mean for r, x, y to be in SAT? Well, it's like for most y, there exists z, the certificate, such that like v, x, y, z equals 1. Like, where v is like the algorithm that like takes as input a purported certificate z and checks whether it satisfies the output of r, x, y. Okay, so the way to rewrite this in the same way would be, for most y, whatever potential, you want to say that the output RxY is not intact, so whatever potential certificate you get, VXYZ is 0. Any questions? So actually, if you kind of look at what we've got here, I rarely use colored chalk, and maybe I'll do it. We have this like kind of quantifier-looking definition of both AM, MA, and AM. So like in MA, it's like if you're in the language, there exists Y. Think of for most as a quantifier. For most Z, this deterministic algorithm X, Y, Z is 1. And otherwise, for all Y, for most Z, this thing equals 0. And similarly here, like this is one way to define AM, it's just quite syntactic. You want it to be that, again, there is a deterministic polynomial time algorithm V, such that when X is in the language, for most Y, there exists a Z, such that VXYZ is 1, and when it's not in the language, for most Y, for all Z, this thing outputs 0. Okay, so it's a little bit syntactic looking, but there you have it. Yep.
Is there some line with like the formals? Like,
Why you can, or
yeah,
you cannot. These are different classes.
oh, whoops, okay.
Yeah. So these are different classes, and it's sort of not clear how they relate to each other. I mean, if you think about them in like the story terms, like here it's like NP, except the verifier can be randomized. Here it's more like the verifier can like challenge the prover with like a random stat question in a way. Yeah.
Is there any way to rephrase one or both of these in terms of like randomized, non-deterministic Turing machines or something?
You kind of think of like V as like you could think if you want as like some kind of non-deterministic polynomial time Turing machine, and like the criterion for like whether it overall accepts is like whether like there is some choice of guesses here such that like for most choices of guesses here it outputs 1. I don't know if that's a satisfactory way to say it. But we will compare these to the polynomial time hierarchy in the class. Okay. So, in fact, let me invent like a new notation for this quantifier for most. Some people use exist plus, which I like, but I'm not going to use it. I'll use instead like this backwards R. So that's the backwards R is like means for most Z. So really, and it really has a parameter like how many is most, but we'll just say it's 2/3. Okay, so this means for at least a 2/3 fraction of Z's. And you might get stressed that like, oh, you picked, I remember that with BPP we defined it in terms of 2/3, but then we saw that it didn't really change things if we changed that number. It's going to be the same situation for these two classes, so it'll be fine that we just fix an explicit number of 2/3.
Where's R?
What's that?
Where's R?
For random.
Oh, okay.
But actually this is like ya or something, right? I don't know why ya, but that's what it is.
Okay.
So, you can get like really into this like defining complexity classes via like quantifier sting, and it gets very syntactic looking. I don't want to do it too much, but like it will be useful for like this class to invent some shorthands. So here's the shorthands. MA, I'm going to say, well, what class is this? It's the class that exists for most slash for all for most. Okay? And like, what is the expansion of this? The expansion of this is this. Okay? So the first segment says what happens when X is in the language. The second segment says what happens when X is not in the language. And like there exists Y such that for most Z, and then it's always like you have V equaling 1 here and V equaling 0 here. Okay, so it's kind of crazy, and we'll probably only do that in this class, but like for today, this will be our shorthand. Okay, so let's figure out what is the shorthand for AM. It's For most y, there exists a z in the yes case. And in the no case, I also call this the yes case in the no case. It's a lot to take in, but it's like for most y, for all z.
You don't need Z, right?
Oh, yeah, so I don't need to. Thank you. The whole point is to try to get rid of it. Okay, so let's actually just warm up so that this is crazy notation. How would I write BPP in this language? Yep,
Just backwards R / backwards R.
that's right. Okay, so like, for a language in BPP, it's like if there's like a deterministic Turing machine, which you think of the algorithm which gets the real input in like the random tape, and when X is in the language, it's supposed to be that for most random strings, V outputs 1, and when X is not in the language, it's supposed to be that for most random strings, V outputs 0. Okay? Test your knowledge. What is NP? Right, it's to exist for all. When you're in the language, there is supposed to exist some certificate Y that makes you say 1. When you're not, it's supposed to be that for all candidate certificates, you say 0. And sigma 2p, I guess you won't be surprised to know it's exists for all / for all exists. And here's like a little cute thing that you can think about for 1 second. Like the co of a class is like you reverse the 2 halves. Okay, so pretty good, like co-NP is for all exists. And co-BPP is for most, which is true, because co-BPP is BPP. BPP is closed under complement. These two classes, neither is closed under complement, obviously. So, okay, there's a lot of craziness on the board, but I just introduced 2 new complexity classes, so I better put them into like a more familiar picture. So we have P. Okay, here inclusion is going to be to the right. So P, everybody knows that's contained in BPP. And it's also contained in NP. The relationship between BPP and NP is not known. Now, kind of both of these classes obviously include BPP, and they also obviously include NP. And it's clear from the stories, like if you just, to see that they include BPP, I mean, it's just like, you just forget about the fact that like Merlin's helping you out with something, you just say, never mind Merlin, and like, random just to calculate the answer yourself. And similarly, like here, like the reduction just does all the work, it's randomized, and then like if it decides the answer is yes, it outputs a trivial side instance. If it's no, it outputs a trivial on-side instance. And it's also clear that these classes include NP, because like whenever you have the power of randomness, you can just not use it if you don't want. Okay, so we have MA, and we have AM, and they both contain both. So one question is, what's up with the relationship between the 2 of them? Perhaps they're the same, perhaps one contains the other, perhaps they're incomparable. Does anybody who hasn't seen it before want to guess? Yes.
So just a question about MA. The Z part is like the randomized part of Arthur, right?
Yeah, it's like a random point for Arthur, yeah. So I guess the intuition is not very clear, right? I'll tell you. It's going to turn out that like MA is a subset of AM. So, okay. So we'll prove that today. So here's some theorems. I should mention that these AM and MA turn out to be pretty important complexity classes, which is why we're spending a whole lecture on them. So today's theorems, we're going to prove a couple, at least. We'll see how far we get. So one theorem we'll prove is that MA is a subset of AM. Okay, so you can verify more languages if like Arthur is allowed to challenge Merlin first, as opposed to Merlin just telling something to Arthur. Yep.
It's like part of the proof going to be because there exists for most, and for most there exists. So in the first case, the Y is there exists certificate is the same for most of them, while in the latter case, the Y would be different, the certificate.
Yeah. We'll see why the proof works, but yeah, it's true that like
quantifier, then it makes sense.
It's hard to say, yeah, like the for most is like sort of halfway between exist and for all.
Yeah.
Somehow I guess the power of like Arthur-Merlin, it will eventually get into like a view of this where it's like interactive proofs, but like here's almost like Arthur gets to sort of ask Merlin a question. Granted it's a random question, but that can somehow still help. Whereas here, it feels like almost the same as NP. It's like basically just some person tells you a proof and like, oh, you can check it with randomness if you want, but like we kind of feel that BPP is the same as P, so maybe it's not so much bigger than NP. I'll talk about that later too, yeah?
So you mentioned a minute ago that MA is not closed under complement?
I mean, it's not known to be closed under
Oh,
complement,
okay.
yeah.
It's-
And it's probably strongly believed to not be closed under complement.
Okay.
Same with AM, yeah.
So does any string of symbols in that language give you like probably different from all the other ones, complexity class and some sort of like oral hierarchy?
Yeah, there's like papers that are written on this, and yeah, you can think about it. So as we'll see, sometimes these hierarchies collapse and sometimes they don't. You can actually throw in like a third quantifier, which is like for strictly more than half, like for majority, and like you can thereby define like the class PP that we've seen before and other such things. You can also throw in like the quantifier like for an odd number of strings, which looks really insane, but it's going to come up later. Okay, so another theorem that we'll prove is the following, which is that this is actually pretty cool. For both MA and AM, they're equivalent to their one-sided error versions. So, you know, BPP is, as a class, has two-sided error, and like if you say, well, I want one-sided error, then you get like RP or co-RP, and like there's seemingly, we don't know how to prove that they're the same. But here, like MA and AM, you can actually prove it's the same as if there's like one-sided error. So let me say more specifically what that means. So let's say for MA, it turns out that, well, I'll use this crazy notation first. It turns out that it's the same as exists for all slash for all for most. Yeah, so to compare it, it's like here on the inside, there's a for all. So what does that mean? Let's expand it out a little bit more in words. It's like when X is in the language, there exists a proof that you know, Merlin can sort of send such that Arthur always accepts. Now Arthur is randomized, always accepts. And the other part, the no case is the same as it was before. So when it's not in the language, whatever Merlin sends, well, Arthur has a high chance of rejecting. Okay. So somehow it's going to like, you know, before like it's just Arthur accepted Merlin's proof with high probability, and like somehow we'll see that like, well, Merlin can send us some extra stuff that will like, you know, really 100% convince like Arthur. So that's cool. And let me write out what it, I mean, for AM, what does it mean? I'll just do it symbolically for AM. So for AM, it's the same as for all there exists, slash for most, for all. So in other words, to compare it to this, our first definition, it's like for all random strings that like Arthur chooses, there'll be a proof that Merlin can give that will be convincing in the yes case. And in the no case, it's the same old thing for like most random strings, or I guess it's like, yeah, kind of here, it's kind of convenient. This random reduction has the property that like in the yes case, you always produce a satisfying formula, which Merlin can convince you of. And in the no case, it's merely that like most of the time you produce a non-satisfying formula, non-satisfiable formula.
What is the difference then if we pick a for most quantifier in the right side and switch it to exist? I mean, like, why the proof for this will not work? Like, it seems like it's the same if you pick the right side quantifier rather than left side.
You want
I want
changes to exist?
Yes, I want.
That's like a downgrade. Right? Like changing this to a for all is kind of like making it like better or like more impressive.
Oh,
Whereas here it's like kind of like a downgrade.
oh.
Yeah, when I was preparing these notes, I like had the exact confusion like a couple of times myself. Like it's, feel free to ask these questions because it's very confusing. Yeah. In my mind, actually, usually when I think about AM, I just remember this. Like, it's not so rare that like you need to remember that it's equivalent to have it's called perfect completeness in the yes case. So was there another question?
Yeah, it's basically the same question. So like, there's no way of getting the no false positives version of this?
You can do it, but like for co-AM.
Okay.
Yeah. So that's another theorem that we'll prove. It's not too hard. And there's some cool corollaries of it. So one, if you just now look syntactically at, let's say, MA, I claim that MA, now we can see, like, syntactically, it's a subset of sigma 2p. Because, yeah, if you have a language, it's an MA, then when X is in the language, there exists a Y such that for all Z, the verifier says yes. That's the same as in sigma 2. When it's an MA, you know in the no case, for all Y, for most Z's, the verifier will say no. So in particular, for all Y, there exists a Z such the verifier will say no. Most of them may say no. And that's what you need for sigma 2p. So somehow just by syntactic reasons, this is like one kind of convenience of the notation in a way, like we kind of get this immediately. Well, let me put that up here. Oh, and I told you by, one thing we're going to prove is that MA is a subset of AM, so let me sort of stretch this to the right. So AM is kind of out here. I guess I didn't really need to draw this, it's implied by this, so I'll undraw it. And yeah, we have like another syntactic thing about AM. I guess you can see, like, if we like downgrade this to exist, then we get that as a subset of pi 2p. But again, it's the same thing. Like in the no case, in the AM, like for most y's, it'll be that for all z we get 0. And so in particular, that means that there exists a y, such that for all z's we get 0. So this is in pi 2p. And actually, particularly this means that MA is in pi 2p. So MA is in both sigma 2p and pi 2p. We don't know about the relationship between these two classes. In particular, this means that BPP is in both sigma 2p and pi 2p. And this is a cool fact that we could have proved earlier, but like I saved it for this lecture so that we can save on proofs. Right, MA is a subset of this one. So a corollary of both of these things is that BPP is in sigma 2p and it's in pi 2p. Okay, and sometimes people just remember that this means it's in the hierarchy. That's kind of like a slightly reassuring. Like BPP, we kind of think of it as like shouldn't be too different from P. It's supposed to be represent efficient computation in some ways. And so it would be kind of disappointing if it was like outside this enormous class, the polynomial time hierarchy. And so this shows that it's not. It's in the polynomial time. Right. So, okay, so I introduced these two classes, AM and MA, yeah?
We don't like really need to downgrade anything, right? Like we can just think of the subsetness relation as like making the quantifier stronger.
Yeah, I guess it's weird that like when you like, I don't know if it's a downgrade or not, or maybe it's an upgrade apparently, but like, yeah, basically when you have like some, if like all your quantifiers like are like weaker / stronger in one direction, then you'll have like a containment relationship.
Right, okay.
It's not super clear, but if you just think about expand out what this means, it's like syntactically sort of immediate that like it implies this.
Right.
Okay. So yeah, I initially said like I introduced these two classes, MA and AM, it was some kind of like randomized version of NP. And in fact, in some sense, the belief is first of all that MA actually equals NP. And why is that? basically, the extent to which this is believed in complexity theory is like sort of identical to the extent to which BPP is believed to equal P. It's really, they're almost very similar, right? Like in both cases, like a prover gives you something, and then you do like an efficient computation. In one case it's randomized, in one case it's not. We're trying to believe that randomness doesn't really help you, BPP equals P, and so that would make these the same too. Later in the course, we'll eventually like see some evidence that like BPP equals P if there exists functions in like a large uniform complexity class that are hard for circuits, which we believe, then we'll show that BPP equals P. And like literally the exact same evidence also simultaneously shows that MA equals NP. So somehow the belief is that this class is the same as NP. What about AM? Well, it's also believed that AM equals NP. I didn't underline it as many times because it's like a stronger belief, naturally. And in the same way that there's this hardness versus randomness evidence that we'll eventually see that makes us think that BPP equals P, if you make an even stronger hardness assumption that like there's a problem in like a fairly low uniform complexity class that's like hard, not just for circuits, but hard for circuits with SAT gates, which we still believe is true, but like it's a stronger assumption, then it turns out that AM can be de-randomized to NP. So, still also believe this, but like it's definitely a slightly weaker belief. But if that's true, then all these classes I'm talking about, they're all equal to NP. In particular, that would put AM inside sigma 2 because NP is in sigma 2. But we currently cannot prove it. Let me also mention that you should hesitate always to introduce new complexity classes. You should only sort of do it for a good reason. But one good reason is like if like there's a problem, like a problem you would care about in the class that's like somehow not in any lower classes. And actually for MA, it's a questionable situation because there are no, slightly going out on a limb, but basically there are no problems in MA that are not known to be in the union of NP and BPP. So, yeah, like we don't really know anything that like, anything in MA that's not either here or here. If you remember like one time on Piazza I talked about like promise classes, there's like a promise version of MA and like there's some very obscure like quantum problem that's like inside promise MA but not inside these guys, but like it's pretty weird. I mean like, so basically, maybe that also furthers our belief a little bit. It's hardly different from NP. On the other hand, AM, it's informally a bigger class. There are like several, like lots. There's several important problems that we know are in AM that we cannot put in anything smaller. Like we can't put them into MA, we can't put them into NP, we can't put them into BPP. So that's why AM is like quite, well, one reason AM is quite important. I won't list them all, but like I'll just say in words a couple. Here's a problem that's known to be in AM. I give you like a bunch of multivariate polynomials. And their coefficients are integers. So you just write down the coefficients of a bunch of multivariate polynomials. And I want to ask, do they have a common root, a common zero, over the complex numbers? That's in AM, deciding if they have a common root. That's interesting. You might a little bit say, like, why isn't it an NP? Like, just can't the verifier just give the common roots for the verifier to check? But there's some issue about like, well, what if the numbers are very large, or like the roots are complex, so like how do you represent them? So you can get around that using AM. Another famous problem that's in, I'll write this out, another famous problem that's in AM is graph non-isomorphism. Or if you like, graph isomorphism is in co-AM. But I'll write it the other way. So this is a fact. The complement of graph isomorphism is in AM. So like graph isomorphism is like clearly an NP kind of thing. It's clearly an NP. You can easily, two graphs are isomorphic. The prover says what the isomorphism is. But this is like a complement of graph isomorphism. It's sort of in an NP-like class. There's somehow like a succinct proof scheme whereby Arthur becomes convinced that two graphs are not isomorphic. Now, possibly you've seen this before in your life in the context of interactive proofs. And like a high-level sketch of sort of how this thing works is, like you're given two graphs, G0 and G1, and you can imagine that like Arthur picks J from 0, 1 randomly, and then sort of tells Merlin random relabeling of G sub j. So picks one of them, like scrambles the vertex names and tells it to Merlin. And then like Merlin is supposed to guess j. Let me talk about this at a high level for a second. There might be some flaws in what I'm going to say. The idea is that if G0 and G1 are isomorphic, there's like nothing Merlin can do. Like there's no way Merlin can guess J because like the distribution of what he sees is the same. But if G0 and G1 are non-isomorphic, there's a difference between them. Then like actually which J Arthur picked is determined. So Merlin, who has infinite computational power, can just literally figure out which one Arthur chose. So it looks like AM. There's a catch though. This protocol, like the reason it works, it heavily relies on the fact that Arthur has so-called private coins. Basically, they're like Merlin, he can secretly pick random bits, like J and also this permutation, and Merlin does not see them. For the proof to make sense, I mean, that's clearly necessary. But the definition of AM is like public coins. If you sort of think about it, you interpret AM the same way. The normal version has like the randomness here. It's like, quantifiers like this is like for most y there exists z, like z can depend on y. So it's like really like, it's correctly modeled by the situation where like Merlin can see Arthur's coin flips. And it looks like that would ruin this, right? Of course, if Merlin can see Arthur's coin flips, then like Merlin is a very easy ball game if it says which it is. But it's a fact that with a more clever scheme, you can get into a situation where you have the same story, but like Arthur has public coin flips. And like it's still the same property that like if they're non-isomorphic, then Merlin can sort of win with high probability. And if they're isomorphic, Merlin cannot win with high probability. Even though like now there's a way where Merlin can even see Arthur's coins. So we'll, I think, see that in a later lecture, but we won't see it for now, but trust me, it's the case. And that shows that the complement of graph isomorphism is MA. Okay. Any questions about that? So, again, it depends how far we get today. We might start talking about this more next time. But there's one more theorem that we'll prove later, some indefinite date, theorem 3, about AM and MA. And it's related to this way of thinking of like AM as like an interactive proof system between Arthur and Merlin. You can imagine like, this was like a kind of interactive proof system where like first Arthur says something, then Merlin says something. It's the end. You can imagine like a more complicated scheme where like Arthur gets to, pick some random things, tell them to Merlin, Merlin, sends a certificate, but now Arthur, like based on that, can like send another random question, and like Merlin can send back an answer, and it could go for like, I don't know, like 10 steps or something. So you can invent a class called like, this class. I can just keep writing. Okay, and this is like a 7-round interactive proof of this form where like Arthur picks some random string and Merlin tells him something and Arthur picks something and Merlin tells him something, and at the end like Arthur makes a decision. And it turns out that this is equal to AM. Okay, so for any finite fixed length sequence of A's and M's, like 10 or 100, but like not N, but like a fixed length sequence, there's like round compression. You can get it down to a 2-round interactive proof. Okay? So this is an example where like you could imagine like start inventing like an even bigger hierarchy of like AM or MA where you start like having lots of alternations like this. Turns out, there's also a theorem of Barak, that it all collapses down to AM. Okay, so that's why like you don't have to remember like all these infinitely many crazy classes, it's just AM and MA. Yeah?
Does it mean that we kind of have in general private coins without changing anything to the complexity class?
Yeah, we'll see this later. So in fact, if in the context of finite round interactive proofs, like 100-round interactive proofs, you can convert any private coin protocol to a public coin protocol at the expense of adding, I think, 2 rounds. But then you just apply this theorem and like compress everything down to 2 rounds.
Okay.
Yeah. So finite round interactive proofs equals AM, and it doesn't matter if it's public coins or private coins, and it also doesn't matter if like you require like, you know, perfect, like one-sided error or two-sided error, it's like all the same. On the other hand, we'll eventually see this, maybe you've seen this before, that if you allow like unboundedly many alternations, like a polynomial length back and forth, that gives you p-space. Well, IP equals p-space. Okay, good. Any more questions? Now we're going to start to prove some things. All right, let's prove some things. Good. So let's prove theorem 1 first. Let me erase this business. Okay, so theorem 1, we want to show that MA is a subset of AM. Okay, so what we're going to do is take a language that's in MA and show that it's in AM. So proof of 1. Okay, so suppose L is in MA. Okay, so again, think of this, it's good to think of this as like maybe the interactive proof way. You know, both Arthur and Merlin are staring at some string X. Merlin's trying to convince Arthur that it's in the language, so Merlin sends some purported certificate about X, call it Y, and then Arthur, does some randomness to try to confirm or deny that certificate. Well, we'll write it all out again. So what does this mean? It means that when X is in the language, there exists some certificate Y that Merlin can send, such that we write in this randomized notation the probability that A, X, Y accepts is at least 2/3. Okay, here A is randomness. Arthur is randomized. This the probabilities over A is coin flips. And when X is not in the language, for all things that Merlin sends, the probability that A, X, Y, and you write it this way, outputs 1 is at most 1/3. Okay. So the first step of this is a step we've seen before, which is error reduction, or success amplification. Okay, so basically at this point in time, like Arthur's holding onto the certificate and knows if it runs a certain randomized algorithm, it'll come to a good answer with probability, except with probability 1/3. So it's just going to do its algorithm 1,000 times and take the majority answer of what it sees, as you do when you're amplifying error probabilities in BPP. And that indeed drives the error down. So okay, let Arthur, you're changing the algorithm here, run its algorithm many times. And take the majority answer. And that boosts, 1/3 in both scenarios, down to, I'll make it something extremely big, like 4 to the minus p of n, where by n, I mean the length of x, and by p of n, I mean the length of y. Okay, so whatever, n always stands for the length of x, y, this quantification is really over some y's of some polynomial length, call it p. And now by using more time than p, basically I'm going to repeat something like order p of n many times. In general, if you repeat, t times, the new error is exponentially minus t. So, I'll have Arthur repeat his verification routine like p of n times so that this error probability gets really small. Smaller than 4 to the minus p. Yeah, that's a trick that we've used a lot with BPP. Right. So, what does this mean? It means I can kind of cross this out and put 1 minus 4 to the minus p here. And let me do that, and also let me, at the same time, convert this notation to a deterministic notation that takes a random string as an input. So what I'm saying here is I'll convert this to for most z, but this for most is really for most. So here I mean at least 1 minus 4 to the minus p fraction of all z's. V of x y, the certificate, this is the random string equals 1. Okay, and here I'm going to convert this to, really for most, I guess same thing, v x, y, z equals 0. Okay, so even if L initially had like an error parameter that was like 1/3, I can, at the expense of a little bit of time, convert the error probability to like 4 to the minus t. Any questions? Okay, so remember, this is like deterministic. You can almost imagine that like V is like a third party called the referee. Okay? And so like everybody is like staring at the string x. Merlin says some string y, cleverly chosen to try to like trick Arthur or to convince Arthur that x is in the language. Then it's kind of like Arthur just like he's like a different person. He just like flips a bunch of coins and says like Z. Okay, and then the verifier, the judge, who's deterministic, looks at Merlin's reported certificate and Arthur's random coins and deterministically says 1 or 0. Okay, and the situation is that there are these three personages such that these two statements about their actions hold. Okay, and if you look at the definition of AM, what are we trying to do? We're trying to show that L is also in AM. It's very similar, except the for all is, or sorry, the for most thing is on the outside. So what we're going to do is just take this exact scenario, but just now let Arthur talk first. Let Arthur say his random string first. But otherwise, then Merlin will look at those coins and possibly just decide what to say based on that. And then the judge V will look at everything and give the output. It's kind of like the same scenario as before. Like Merlin's going to say something to Arthur and he's going to randomize, but Arthur's just like, I'll tell you what, these are the coins I'm going to use. There you go. You can have that information. And what I want to say is that we'll have the same property. Like if x is in the language, in this new scenario, it'll still be the case that, well, for most choices of Arthur's strings, there'll be an exist of y such that the verifier will say 1, and conversely. Okay, so I've kind of just reversed things, and that will show that it's in AM. So let's think about these two situations. Let's consider first the easier case, when x is in L. Okay, it used to be the case when x is in L that there's something convincing Merlin could say so that most things, most random choices of Arthur would lead to acceptance. This is kind of this is a case where Merlin is trying to win. Merlin wins. Merlin's always trying to convince that x is in the language. So now Arthur's preemptively blurting out his coin sequence. That's fine. Merlin's fine. I don't even care. I'll just say the same y I was always going to say. For every x that's in the language, there is some good y that makes Arthur accept the probability. Merlin's whatever your coin flips are, I'm just going to say that y anyway. So it doesn't matter that we reverse the quantifiers to Merlin. It'll still be the case that for this many fraction of z's, the verifier will output 1. Okay, so Merlin just says the same y he was going to say before. Okay, and this verifier is outputs 1 with high probability. Okay, what about when x is not in the language? And here, it looks like potentially Merlin's got an advantage. Maybe he can trick Arthur, or trick the verifier sort of into accepting even though x is not in the language. Right? And now, Merlin gets to see the coin flips Arthur is going to use. So he can maybe deviously choose the y to send based on the coin flips that Arthur sends. But it's not going to help. Okay, so here's the situation. Right? After we did this error boosting trick, let's consider the land in which the z's live. Okay, so z's live in some, this blob is 0, 1 to the r of n, where r is how many coin flips Arthur makes now. And this is saying in particular when x is not in the language, we know that for every certificate, every supposed certificate y, there's very few z's, like very few z's where v gives the wrong answer, namely 1. Okay? So for every y, like maybe for one particular y, like here's the very few z's, this blob is like the very few z's where v says 1, which is wrong. And then for some other y, you know, there could be some other like z's where v gives the wrong answer. So this is like z's such that, you know, v x, y, z equals 1 wrongly. We're assuming that x is not in the language. And like for each blob is associated to a different y. So like there's another blob, but what is the point? There's only, you know, for all the possible y's, of which there are 2 to the p of n, right? At most, a 4 to the minus p of n fraction of z's lead to the wrong answer. Namely, v says 1. Okay, so we can just like take the union over all of them, and still, like the union over all of them is like a negligible fraction of the z's. Okay, so let me write that down. By the union bound, except for 2 to the p times 4 to the minus p, which is 2 to the minus p fraction of z's. Let's say except this many fraction of z's. R, x, y, oh, not R, v, x, y, z is 0 correctly. Simultaneously for all y. Right, we have that like for all y, for almost all z, except for like 2 to the minus n fraction, v, y, x, y, z is correctly 0.
It should be reversed.
Sorry. Thank you.
So for most z,
Okay, so it's like the punchline was exactly wrong. Right. Okay, what was the story here actually? I didn't write it, so let me write it. It's like for almost all z, there still exists a y such that v, x, y, z equals 1. And it's like y doesn't even have to depend on z, even though we now allow it to. Okay, so, and this is at MA, I hope it's still, oh sorry, this is AM. No, it's no longer up there. But AM was like, for most exists, for most for all. Okay, any questions about this? Yeah?
Can you repeat the argument for the boosting to that probability?
Sure. So we're previously in the situation where given a y, okay, when x is in the language, there is some y such that this randomized algorithm outputs the correct thing, except with probably at most 1/3. And in this case, no matter what the y says, the randomized algorithm gets the wrong answer again with probably at most 1/3. So like it's sort of always the case that like this randomized algorithm is over some coin flips is like getting the right answer except with probably at most 1/3. So it repeats, you know, it just repeats itself t times with like independent coin flips. So that, you know, x and y are now fixed, and it, you know, it runs itself with random coin flips, or like t many z's, if you will, and it takes the majority of the answers. And if each answer was like, you know, if the answers had a certain bias, either towards 1 or 0, such that they equaled that 1 or 0 value with probability at least 2/3, then when you repeat it like t times and look for the majority value, it's like really, really likely to be the bias case. So at some point, like once x and y are fixed, we know that A has the property, if you think of like A as like a random variable, it's one of two cases, either like probability that A equals 1 is at least 2/3, or maybe probability that A equals 0 is at least 2/3. But now we're using the fact that like if you draw from a random variable that's like bias, if you like flip the bias coin like many times independently and take the majority answer, that majority answer will also be biased in the same way, either towards 1 or 0. And the bias will be extreme, like it'll almost surely be 1 or 0. And so like with polynomially many repetitions, which only costs us time, nothing else, polynomially many repetitions, well, and random coins, but we don't mind, we can get this error bound down to like something exponentially smaller. Okay, any more questions? Yep.
So why can't you use an argument like this to show the reverse inclusion?
Let's see. So we have a language that's in AM. So like Arthur flips some coins, or like asks Merlin a random question, and Merlin sends back an answer. Well, it's like Merlin's answer could depend on the random coins, and that like somehow might be essential. Like, I don't know. I mean, Merlin cannot just. Because it's sort of because like you can't boost it for existence. Like Merlin, you know. It could be that like when Merlin's giving a certificate back to Arthur, like there's just like one certificate that works and every other certificate doesn't work. And so like it might be that like for each random choice of Arthur, there's just like a unique like one certificate that like Merlin can send that's good. And so like overall in the certificate space, like there are very few certificates that are. You need like basically you need like a certificate that's like sort of globally good for like most choices of Arthur's coin flips, and there's no reason why there should be such a thing.
Yeah, like the like with the graph and isomorphism example, like there it's very clear the certificate depends on what Arthur's coin flip is, right? Because it should match what the coin flip is the right certificate. So.
Yeah, it's a little unclear because of the public-private coins thing, but if you don't worry about that too much, then
yeah,
like, yeah,
I'm
it's
assuming
like
private coins, I guess, right?
it's like hard for like Merlin in advance in the graph isomorphism thing. Even let's say you just worry about private coins. It's hard for like Merlin in advance to like send a certificate that like Arthur can check. It's hard to say, but yeah, I'm not sure we can give like a really compelling explanation except that it doesn't work.
But I guess also the caveat being that we believe these things are equal anyway, so.
Well,
yeah.
yeah. But for trickier reasons, for AM than for MA. Okay, so now let's prove 2. Okay, so as I mentioned, corollaries of 2, well, in fact, corollary of just this, that MA is in this class, this implies that it's in sigma 2p. And so a corollary of all this one-sided error stuff is that BPP is in sigma 2p. And also pi 2p, but actually it's enough to, if you want to show that, it's enough to prove that BPP is in sigma 2p. Because BPP is close in a complement. So by taking the complement of both sides, you get BPP is in the complement of this class. So I'm actually just going to start out, I'll just prove this directly, and then at the end we'll kind of observe this, that you can also get one-sided error for an M. So let me just start proving that BPP is in sigma 2. Okay, so let's show BPP is in sigma 2. It kind of a little bit has a flavor of like getting rid of error. Like this is a randomized class. This class, depending on when you look at it, is not randomized. It's hard to say, but right. This fact, by the way, is called the Sipser-Gotts-Lauterman theorem. This was proved like a long time ago before MA and AM were invented. Okay, so what we have to do, well, say L is a language in BPP, and I'll have to show that L is in sigma 2. Okay, so, well, what does that mean? It means that, okay, if X is in L, means the probability over, say, the random points of some randomized algorithm, BXR equals 1 is at least 2/3. And similarly about when X is not in L, here B again is like a deterministic algorithm. You think of this as like a randomized algorithm where R are the coin flips. And the probability over R is P. It's like P of n, by the way. It's like some polynomial in the length of X. BXR equals, say, 1 is at most 2/3, 1/3. Yeah, that's what L and DBT means. There exists some polynomial B and some polynomial time machine B with these properties. Yes?
So maybe you're going to get to this, but it's not clear to me why showing that BB is in sigma 2B shows that MA is equivalent to its consecutive error version.
Yeah, it doesn't. So I'm proving a corollary of this, but like once we see the proof, it'll kind of become not hard to see why we can also get this data. Okay. Yeah. Yeah, it's not direct at all. Okay, good. So the first thing we do is like it's always a safe move in all these arguments is to just boost this up to like a much better number. So just automatically do that. So it turns out that like this is going to be fine. 1 minus 2 to the minus n and 2 to the minus n. Always a safe move. Okay. Remember, like you cannot like make this parameter, the exponent here, fundamentally better than the number of coin flips you use, because in order to boost, like you have to use more coin flips. So yeah, but that's okay. 2 to the minus n will be fine. Okay, so there's going to be a picture that's sort of similar to this, but like it's a bit trickier. So let's draw two pictures, depending on what world we're in. In the world where X is in L, and the world where X is not in L. Now this box is going to be my schematic diagram of all the R's. Okay, in other words, it's 0, 1 to the P. Now a similar schematic diagram, I don't know why it's a rectangle, but for all the R's. And what are the two facts we know? Let's look at all the places, let's shade in all the region. This will be shading, oh I could use color, well, never mind. Yeah, why don't I do that, it'll be fun. Let's shade in all the region where, and I'll call this S, the shaded region, I guess that's the shading, where BXR equals 1. It's all the R's. Okay. So what do we know? We know that when X is in L, almost all the R's make B say 1. So like S is like some enormous set. It's like a huge fraction of everything. Okay. And on the other hand, when X is not in L, the set S is like something very tiny. It's like some very tiny fraction of the space. Okay? And somehow we have to distinguish between these two cases. And we have the power of sigma 2. So what we're trying to do is like show some kind of like sigma 2 style algorithm that can kind of distinguish between whether these two whether this set is enormous or small. But we kind of only know the set implicitly. We know the set S implicitly through saying, well, it's all the R's that make this V say 1. So how are we going to do that? This is like a clever trick comes in. At the highest level, the distinction is going to be this. We're going to imagine like taking this shaded set and somehow imagine like shifting it around a few times, not too many times, but shifting around it a few times and taking the union of the shifts. And like pictorially, like if you shift this around a few times and take the union, like you get a very small set. But if you take this enormous set, shift it around a few times and take the union, I want to say that like there's a good chance you'll get everything. Like not a single point will be outside the shift. Okay, and that ability to get like everything is going to be like good. There's like somehow no error there. Well, it's a high level picture. But see how it goes. So let me make a definition. Say the translate of a set S by a string W. It's, which I'll write as W XOR S. It's just all the strings of the form W XOR R for R in it. Okay, this is a pointwise XOR of these two strings. Okay? And this really is like a sort of a shift in the sense that, like, observation, this set, the shifted set has the same cardinality as the original set. Okay? Because like this is like shifting by, or XORing with W is like a one-to-one match. Okay? It's a bijection, so it really just moves the set around, but doesn't change its size. And now, the idea in this proof is just consider a set called U, which, as I said, is like a union of a bunch of shifts of S. And I'm actually going to consider a number of shifts which, somewhat by coincidence, is exactly equal to P, or P of n, okay, which is a polynomial amount. Okay, I haven't said what these W1s, these are all different strings, W1 through WP, but like, given a bunch of different strings W1 through WP, let me just kind of imagine this set U, which is the union of the shifts of S by the W's. And I'll imagine the two, what could be up with U in the two cases, and I'll start with this one because it's the easier case. So, 2 points here. So let's say, if S, this is the second case where X is not in L, if S has density that goes 2 to the minus n, by density I just mean the fractional size of S within its surrounding world. The fraction of strings in 0, 1 to the p that are in S. It has density at most 2 to the minus n. Then the density of U is, well, it's at most p of n times 2 to the minus n, which is equal to tiny, for any strings W1 through WP. Okay, it doesn't matter if the translates overlap or don't overlap, it doesn't matter. Like, even if they all totally don't overlap, the density of the union is still tiny. On the other hand, let's say if density of S is huge, 1 minus 2 to the minus n. Now I'm going to imagine what happens if the W's are chosen randomly. Okay? I really actually just want that there exists a choice of W's that will make U be everything. But I'm going to prove that existence by the probabilistic method. Just pick the W's randomly and actually show that, like, with high probability the union is everything. Okay, so if they're random, oh yeah, and W1 through WP are random and independent, I want to say that then U is probably everything. Okay, let me just do that calculation on this little board over here. So it's the usual probabilistic method kind of thing. Let me fix one particular R. There's some R here, and I'll just argue that, like, when I form U in a random way, it's very, very, very likely to include R. So we do that by looking at what's the probability over these shifts that U actually does not contain R. Well, right, R is outside of U if it's outside Wi plus S for every I. And like R is not in Wi plus S. This is equivalent actually to R plus Wi is not in S. Because like this addition is commutative. Mod 2. And for every fixed r, when wi is chosen at random, this thing is a purely random string. It doesn't matter what r is. If you're going to like flip each coordinate with probability of half, as you're doing here, you get a purely random string. So for a fixed r, the probability that this thing is not in S is literally like 1 minus the density of S. It's 2 to the minus n. And the wi's are independent, so like the chance that even like w1 plus s contains r is very small. And now we're doing this experiment like p times. So it's at most 2 to the minus n to the power of p n. Okay? 2 to the minus n p. Okay, that's just for one fixed r. The probability that goes wrong is extremely small. That fails to be in U. And now it's so small we can afford to union bound over R. Okay, so union bound over the 2 to the p many r's. And we get the probability that U misses anything. So at most 2 to the p times 2 to the minus np. Which is 2 to the 1 minus n p, which is tiny. Okay, so let us summarize what we have determined. I'm going to erase this. So therefore, what have we shown? When x is in L, well, that's the harder case, but okay, when x is in L, we actually know that for almost all choices of W1 through WP, U contains all strings from this box. And we could phrase that as for all R, R is in U. This, by the way, this is quantification over polynomially many bits. This is also quantification over polynomially many bits. Cool. And we also know that when x is not in L, for all W1 through WP, U is not everything. In fact, U is far from being everything. Most R's are not in U. Even the union is tiny. In fact, we know that like most R's are not in U. And this looks good. We've got some quantifiers. What's up with this R and U? Well, this such a statement, R and U, is a polynomial time deterministic checkable. Right, so I mean, R is in U if and only if either W1 plus R is in S, or W2 plus R is in S, or dot 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 up to WP. And what is the meaning of something being in S? It's this. Okay, so in other words, that's if and only if the or, this is like a big V, the or, I goes from 1 to P of, oh, this is, wow, okay. Or, I goes from 1 to P of V, X, and Wi plus R. That's it. Okay. And, that's equal to 1. So, V is a polynomial time algorithm. So, like, if you're given W's and R's, and you know X, of course, then you can check this in deterministic polynomial time. Okay, so I could imagine that like V prime is the algorithm that does this, and I could replace this statement with V prime of W's, well, X and W and R. And this would be V prime of X, W, and R equals 0. Okay. So therefore, we've sort of visibly shown what? We've therefore, visibly shown that VPP within the class called for most, for all, slash for all, for most. This theorem is sometimes called decisive BPP. Like this is like some other complexity class they call like decisive BPP, but in fact it's equal to BPP. Rather BPP, yeah. And now we just use the syntactic property, right? Like all along we were only trying to show that it's in sigma 2p. So like here it's actually for most w's, for all r this, but in particular that means there exists w's such that for all r this. And similarly, when x is not an L, we know that for all w's, most r do this. So in particular, for all w's, there exists an r which does this. So, syntactically, this is a subset of exists for all and for all exists, which is sigma 2. In other words, if I just remember that this for most was at least there exists, then I would have shown it's in sigma 2. So that checks off this box. And as I said, you can take the co of both sides and get like, well, BPP is a subset of for all for most, slash for most for all, which is a subset of sigma pi 2p. But remember also, let me remember, it's like a long notation, but this thing, this is sort of for all, sorry, for most. So you kind of, if you believe that these like letters, you can just manipulate them, you actually have to be careful, but it sort of says that like for most is like a subset of for most, for all, for most. So let's think about this here. Let's go back to MA. One thing what was I trying to show all along? That even MA is supposed to be in sigma 2. So what is MA? Well, MA is like there exists for most slash for all for most. Yeah, it's actually better than that because we showed one-sided error. It's even this, but just go back to the original. You basically kind of want to replace this like for most part with, which is BPP, with this. Okay? So, you can do that, but you have to think about why it's true, but it is true. So like somehow, using what we just showed, we can replace this by there exists, then for most, for all, and then for all, for most. It's not immediate, but you have to think, basically, in the definition of MA, right, like first Merlin says something to you, and then basically you run a BPP computation. And we kind of showed that like, well, you can convert a BPP computation, this like more complicated thing where you have for all, for most, for all. Okay? So if you just, it's an exercise, but like it's okay. And now you can like merge quantifiers. So like, we've seen this before, like if you have for all something, for all some more stuff, like that's really just for all. And here you can weaken, so like if there exists something, and then like for most subsequent things, in particular, we saw this before, right? You can like weaken a for all to exist and get inclusion. So we get like the subset of exists, so we have exists for all, slash for all exists, okay, which is sigma 2. Okay. We have one more minute. Let me say, I told you I was going to show you the AM version that is in Pi 2. That sorry. This is not all I wanted to show. Yeah. I should have kept the for all here, or for most here. Sorry. This was kind of the conclusion of one-sided error for MA. We got that MA is a subset of this, which is the one-sided error version. Like after Merlin speaks, in the yes case, all of Arthur's random choices give it the right answer. And In the no case, it's just for most. Okay, and then I guess the fact that it's in sigma 2 is a bonus, but this is what we were trying to prove. For what? A one-sided error for AM, for MA. Now I also told you that there's one-sided error for AM. And what was that? We're trying to show this. Sorry. For all exists, slash, for most for all. Okay. So you might sort of say like, well, we can just kind of do it, right? Like, what is AM? The normal version of AM is sort of for all, keep saying for all. It's for most, there exists, slash, for most, for all. So like, for most choices of Arthur, like Merlin, that's the right property. And we want to boost this up to for all. You get one-sided error. And you might kind of think like, oh, we kind of have like a for most situation at the beginning. So like by this, we feel like we can change it to this at the beginning. So like, we're hoping that this is a subset or equal to. It would be for most, for all, there exists. Get a little confused here. Slash, for all, for most, for all. Wait, what? Oh, I know what I have to do. I have to use this one. I'll do it next time. The point is, by the closure of BPP under, I'll do it real fast, but then I have to talk about it more in detail next time. By the closure of BPP under complement, you can also show that it's a subset of the complement of this, which you get by reversing these. So for all, for most, for all. We'll go over this again next time, but then you plug this in for like the R's, you get for all, for most exists, and for most, for all, and that's what you want. This is like weakened to for most, for all, and this is, you can merge these two to there exists and get for all exists. Okay, that was pretty fast, but I'll say it next time. You can get in this way that AM is contained in the one-sided error version, which is this, except that it's sort of cheating. It's not clear that, like, if you think about it long enough, it's clear that you can replace the for all when it's at the end. It's actually not so clear that you can replace it at the beginning because it has something to do with error amplification. So it works, but it requires a little bit of an extra argument. We'll see you next time.